The human brain is an extraordinary organ, a marvel of nature that has fascinated scientists for centuries. It can process vast amounts of information, solve complex problems with ease, and learn and adapt to new situations in ways that are still not fully understood. And it does all of this with remarkable efficiency, far surpassing any man-made machine. Our brains use very little energy. In fact, they consume about the same amount of power as a small light bulb. They are more efficient than any computer we have ever built, operating on just a fraction of the energy. Scientists and engineers have long been fascinated by the brain, intrigued by its capabilities and complexities. They want to understand how it works, how it processes information, and how it can be so efficient. Their goal is to build machines that are as powerful and efficient as our brains, machines that can think, learn, and adapt. This quest has led to the development of a new field, neuromorphic engineering, which combines neuroscience and engineering. Neuromorphic engineering aims to create computer systems that mimic the structure and function of the human brain, systems that can process information in a similar way. Imagine a computer that can learn like a child, absorbing new information and experiences, recognize patterns like a detective, identifying connections and making sense of complex data, and make decisions like an expert, using logic and reasoning to solve problems. This is the promise of neuromorphic engineering, a future where computers are not just tools, but intelligent partners in our quest for knowledge and innovation. As scientists and engineers continue to collaborate, the boundaries of what is possible are constantly being pushed. Advanced neuromorphic systems are already being developed, showing promise in fields ranging from medicine to robotics. The future applications of neuromorphic engineering are vast and varied, with the potential to revolutionize industries and improve our daily lives. Imagine a world where intelligent machines assist us in our work, enhance our creativity, and help us solve the most pressing challenges of our time. This is the vision of a future shaped by the marvel of computation, where the line between human and machine blurs, and the possibilities are endless. Neuromorphic engineering is a new approach to computing that mimics the architecture and functioning of the human brain. It is fundamentally different from traditional computing in several significant ways. Traditional computers process information sequentially. They execute one instruction at a time, following a linear path. In contrast, neuromorphic systems are designed to process information in parallel, much like the human brain. This means they can perform many operations simultaneously, leading to faster and more efficient processing. Traditional computers store information in separate memory locations, which can create bottlenecks and slow down processing. Neuromorphic systems, on the other hand, store information in the connections between artificial neurons, known as synapses. This method is similar to how the human brain stores information in synapses, allowing for more dynamic and flexible data handling. This distributed approach to memory storage makes neuromorphic systems more robust and adaptable, capable of handling complex tasks with greater resilience. Neuromorphic engineering is still in its early stages, but it holds immense potential to revolutionize many fields, from technology to everyday life. These fields include artificial intelligence, where neuromorphic systems can enhance learning algorithms and decision-making processes, robotics, where they can improve the autonomy and efficiency of machines, and medicine, where they can lead to breakthroughs in understanding and treating neurological disorders. As research and development continue, the applications of neuromorphic engineering are expected to expand, leading to innovations we can only begin to imagine today. Collaboration between scientists, engineers, and technologists will be crucial in unlocking the full potential of this groundbreaking field. The vision of a future shaped by neuromorphic engineering is one of smarter, more efficient, and more adaptive technologies that can transform our world in profound ways. As we stand on the brink of this new paradigm, the possibilities are truly limitless. Neuromorphic chips are designed to mimic the structure and function of the human brain. These advanced pieces of technology are at the forefront of artificial intelligence and machine learning. They consist of a large number of interconnected nodes, which are called neurons. These artificial neurons are designed to replicate the behavior of biological neurons found in the brain. Neurons communicate with each other through electrical signals known as spikes. These spikes are crucial for transmitting information across the network of neurons. Each neuron receives input from many other neurons, creating a highly interconnected and dynamic system. This interconnectedness allows for the processing of vast amounts of information simultaneously. These inputs are weighted, and the weights determine the strength of the connections between neurons. The weights can be adjusted based on learning and experience, similar to how synaptic strengths change in the human brain. The neuron sums up its weighted inputs, and if the sum exceeds a certain threshold, the neuron fires a spike. This process is akin to the way biological neurons integrate incoming signals and generate action potentials. This spike is then sent to other neurons, propagating the signal through the network. The transmission of spikes is fundamental to the operation of neuromorphic systems. This simple yet powerful mechanism allows neuromorphic chips to perform complex computations. By leveraging the parallel processing capabilities of neural networks, these chips can handle tasks that are challenging for traditional computers. They can recognize patterns, learn from data, and make decisions. This makes them particularly useful in applications such as image and speech recognition, autonomous systems, and adaptive control. Neuromorphic chips use a different language than traditional computers. Traditional computers use binary code, which consists of zeros and ones. Neuromorphic chips use spikes, which are short bursts of electrical activity. The timing and frequency of spikes carry information, similar to how the brain uses spikes to communicate. The connections between neurons are called synapses. Synapses can change their strength over time, a process known as synaptic plasticity. Synaptic plasticity is the key to learning and memory in neuromorphic systems. By adjusting the strength of synapses, neuromorphic chips can learn to perform new tasks. Learning from experience. Neuromorphic chips and AI. Neuromorphic chips are ideal for artificial intelligence applications. AI systems need to learn from data. They need to adapt to changing environments. Neuromorphic chips can do both of these things. One of the key advantages of neuromorphic chips is their energy efficiency. They use very little power. This makes them ideal for use in mobile devices and embedded systems. Neuromorphic chips are also very good at processing sensory data. This makes them suitable for applications such as image recognition, speech recognition, and natural language processing. Robots with brains. Neuromorphic engineering in robotics. Neuromorphic engineering has the potential to revolutionize robotics. Robots equipped with neuromorphic chips could navigate complex environments. They could interact with humans in a more natural way. They could even learn new skills on their own. Traditional robots are programmed to perform specific tasks. They follow predefined instructions. Neuromorphic robots, on the other hand, could learn from their experiences. They could adapt to new situations. This would make them much more versatile and adaptable than traditional robots. From vision to speech. Diverse applications of neuromorphic systems. Neuromorphic engineering has a wide range of potential applications. In addition to AI and robotics, neuromorphic systems could be used in medicine, finance, and security. For example, neuromorphic chips could be used to develop prosthetic limbs that can be controlled by the brain. They could also be used to create new types of brain-computer interfaces. In finance, neuromorphic systems could be used to develop more sophisticated trading algorithms. In security, they could be used to improve facial recognition systems and detect anomalies in surveillance footage. The future is neuromorphic, a revolution in computing. Neuromorphic engineering is still a relatively new field, but it is rapidly evolving. Researchers are constantly developing new materials and architectures for neuromorphic chips. As neuromorphic technology matures, we can expect to see even more innovative applications. Neuromorphic computing has the potential to revolutionize many industries. It could change the way we live, work, and interact with the world around us. The future of computing is neuromorphic. Join the revolution. Explore the world of neuromorphic engineering. The world of neuromorphic engineering is full of exciting possibilities. If you're interested in the future of computing, I encourage you to learn more about this fascinating field. There are many resources available online and in libraries. You can also find courses and workshops on neuromorphic engineering at universities and technical institutes. Join the revolution and explore the world of neuromorphic engineering. Stay connected. Subscribe for more on the future of AI and its advancements. Thank you for joining me on this journey into the world of neuromorphic engineering. I hope you found it informative and engaging. If you would like to stay up to date on the latest developments in AI, robotics, and neuromorphic computing, I invite you to subscribe to this channel. Together, let's explore the future of intelligence and innovation.